Hello, we are Group 6, our project about audio noise reduction using FIR low pass filter. And Group 6 members are Andrew Harvin, Homam Suleiman, Datshan Murali, Osama Miglid, Suvinch Prasad, and Saleh Abdurrahman. In introduction to our presentation, the digital signal processing DSP serves as a theoretical and computational cornerstone of modern engineering, bridging the gap between natural analog phenomena and digital computation by converting continuous waveform into discrete digital formats. Engineers can deploy powerful programmable software algorithms to filter noise, extract critical information, and enhance overall signal quality. This programmatic approach delivers a level of precision and operational flexibility that traditional analog circuit cannot match. In our project, we apply these principles to audio noise cancellation. We have desired signal 300 Hz clean audio tone and interference 2500 Hz high quality noise and goal algorithmic extraction and noise suppression.
Hi everyone, my name is Andrew Harvin. So now I'm going to present the role and function of the process DSP algorithm. So they have three phases. So first we look the phase one, which is signal digitalization and conditioning. So raw analog input capture via sensor. The second thing, conversion into the digital stream using an analog to digital converter. The third thing is initial anti-aliasing filtering to condition the data. In the phase 2, target manipulation and filtering, which is implement an additive input impulse response filter operating in the time domain. The second thing, mathematically suppresses noise frequency while preserving target features. The third phase is information extraction and interpretation. Execute the features extraction routine once the signal is purified. The second thing, isolate the peak amplitude, frequency shift, or transit anomalies to provide a clean and actionable waveform. Thank you.
Okay, for this project, the methodology applied, we have entirely used the software like using a MATLAB. Okay, so because of its high performance and also computing capabilities to implement the DT system architecture. So the development begins with the mathematical signal modeling to simulate and import raw analog inputs. It's like directly mirrored to the Newton-Shannon sampling theorem through the definition of DT vector and also sampling frequency, which is 8 kilohertz. So by leveraging this framework, which is a programmer, also the system provides a control environment. So we're able to evaluate the algorithmic performance, also analyze stability, and also verify the characteristic which are prior to the final verification. So as we can understand, the MATLAB and signal processing toolbox, it utilizes the software component, specifically employing functions like filter or FFT to execute DSP algorithm, and also it translates mathematical Z transform to discrete linear constant coefficient difference for finite impulse response, which is FIR filtering. So frequency domain shift execute a computationally efficient relation of the discrete Fourier transform, which is DFT, to FFT function to shift the system analysis from time domain to frequency domain. This enables the visualization of a pole zero placement for stability checking and verifies resulting system attributes through magnitude and so phase response plots.
Hello, I am Osama. Today I would like to present the time domain. We analyze the signal in the time domain. The red waveform represents the corporate input signal. It contains the clean 300 Hz audio tone mixed with high frequency noise at 2500 Hz. Because of this noise, the red signal looks distorted and has many fast ripples. After applying the FIR low pass filter, we get the blue waveform. The blue signal is much smoother and cleaner. This shows that the filter successfully removed most of the high frequency noise while keeping the main 300 Hz audio signal. We can also notice a small delay at the beginning. This is called group delay for our filter. The order is shorty and sampling frequency is 8000 Hz. We using the formula Tg equal N over 2 Fs, Tg equal 40 over 2 multiply 8000, we get 2.5 millisecond. So the output signal becomes stable after 2.5 millisecond. This delay is normal for the FIR filter. Overall, the time domain result proves that filter work correctly because the noisy signal become clean and smooth filter. That's all for me. Thank you so much for your attention.
Hello. In this slide, we analyze the signal in the frequency domain using FFT. Before filtering, the spectrum shows two main frequencies. The first one is 300 Hertz, which is the desired audio signal. The second one is 2500 Hertz, which is the unwanted high frequency noise. We used a low pass FIR filter with cutoff frequency of 800 Hz. This is mean the frequency below 800 can pass, while the higher frequency are reduced. After filtering, the 300 Hz signal remains, but the 2500 noise is strongly suppressed. So this result confirmed that FIR filter successfully remove the noise and keep the signal the original audio signal. Thank you.
So for the conclusion, there are main 4 points we have done. So the first is the filter strategy, the design of our project. To achieve the absolute stop band suppression, we deployed a low pass FIR filter to setting a strategic cutoff frequency at 800 Hz. The second would be the complex problem solving, the fix we have found. So during the development, we encountered severe audio lag and distortion. So we resolved this by switching to a balanced linear phase filter, which successfully kept the system fast and stable. For the third would be the theoretical element, which is for the time domain result. So our results were perfectly dis- validated discrete time group delay theory, showing that the reconstructed outputs flawlessly track the 300 Hz sinusoid after a minor 2.5 millisecond delay. And then the fourth and final would be the spectral validation for the frequency domain result. So the 300 Hz target passed through completely unattenuated at a magnitude of 1.0, while the 2500 Hz noise spike was completely flattened to zero. So we have successfully designed a MATLAB-based noise reduction system that isolated a 300 Hz tone from a 2500 Hz noise spike using a windowed FIR filtering and FFT mapping. So the empirical results perfectly validated the DSP theory, achieving absolute stop band suppression and flawless target tracking after predictable 2.5 millisecond group delay. So that's all from our group. Thank you very much.